So, last time we were talking about asymptotic bounds. We showed that for very large block lengths there is a certain region where the best codes are to be found, and I will not dwell on that since that lecture is available to you. And after finishing the section on asymptotic bounds, we went on to talk about decoding techniques, and we said that a principal goal in decoding is to actually try to minimize the probability that you will decode a code word in error, which is very natural. And then we saw that the minimum probability of error decoder first of all reduces under the assumption that all the code words are equally likely, which is often the case, to maximum likelihood decoding. That is, you choose that code word which is such that y given x is the most, y being the received vector, x being the code word. And in turn we reduce that to the minimum distance decoder, that is, you simply decode to the nearest code word, in nearest in the sense of Hamming distance. And I think this is something that we discussed right in the beginning, and in a sense you would have said, well, that is obvious, and that is true, it was obvious even then, but we needed to actually go through the motions of actually proving it. So, then with that preview, let us go back to that review, let us go back to our present lecture, and I am going to call this standard array decoding. So, this will be our lecture 14. All right. So, recap from the last lecture, we looked at asymptotic bounds, and then we talked about the minimum probability of error decoder, and this led us in turn to the maximum likelihood decoder, and again in turn this led us again in turn to the minimum Hamming distance decoder. And as abbreviations, let me abbreviate and write this as MLD, that is very commonly employed, and we will refer to this as the MDD, or the minimum distance decoder. So, our starting point is in fact the minimum distance decoder. Let us adopt the following channel model. That is, that you transmit a code word C, there is additive noise that is added to it, and then what you actually receive is Y. Now, we are still operating over the binary symmetric channel. Where the crossover probability is epsilon, and let me make one change here. Let me call this vector E, and basically the way to make a connection between the binary symmetric channel model here and this additive channel model here is just simply to say that this error vector has a value equal to 1 precisely when there is an error over the channel, in transmission over the channel. The minimum distance decoder chooses C hat, and by C hat we will mean the decoded code word, such that and I have told you that I will abbreviate this by S dot T dot, such that the Hamming distance between y and C hat is a minimum under the restriction that C hat belongs to the code. Okay. So, this script C here denotes the code. Now, in turn, this is equivalent to saying, and I will illustrate this with a picture. So, let us say you have the set of all n tuples here, and somewhere in here you have the received vector, and there may be competing code words. So, there is a code word x 1 and there is a code word x 2, and what you are trying to do is you are trying to decode to that code word which is closest in Hamming distance. Okay. So, what we do is we compute, one way of finding the closest code word is to actually compute y plus x 1, and let us say that this vector is E 1. So, we could compute y plus x 1, we could also compute y plus x 2, and let us say we call this E 1 and this as E 2. The reason that we are writing E 1 and E 2 is because these, I mean, if x 1 was the transmitted code word, then E 1 would actually be the corresponding error vector. So, in that sense, when we add the x's to the y's, what we are actually getting is a list of the potential error patterns, and now what we want to see is which is the closest code word, but that is completely equivalent to saying what is the error pattern which has the least Hamming weight. Okay. So, we have now made a subtle shift, and instead of looking for the closest code word, we are saying let us look for that error pattern whose Hamming weight is the least. Okay. So, and if you want to actually pictorially view this, you can think of this as though there was a line joining these two, and this line represents E 1 and this line over here represents E 2, and what we are really interested in doing is finding that code word whose corresponding error vector has least Hamming weight. With that as background, now I think you will agree that what I am going to write down now is a completely equivalent decoding algorithm. Thus, the decoding algorithm, this is the minimum distance decoding algorithm, can equivalently be phrased as follows. Step 1, form the set y plus c, which is defined to be y plus c where C belongs to the code. So, this is actually a set, and which is obtained by adding to the received vector y all possible code words. So, we form the set. Step 2, now remember I told you that you think of each of these elements as possible error patterns, okay, as potential error patterns. Let E hat be the element in y plus c having least Hamming weight. Step now, of course, there is always this question in your mind, well, what if there are two vectors whose Hamming weight is the least? Then what you do is you can arbitrarily toss a coin. So, it does not really matter at that point. Okay. So, with that in mind, let us just pretend that there is only one. Then we go on to the next step. Step 3, the decoded code word C hat is then given by C hat is equal to y plus E hat. And if you think about it, in some sense what you really are doing is you are saying that, you know what, trying to estimate the code word is really the same as trying to guess what the error pattern was. And in a sense it may be easier to actually find the error pattern, find out what the most likely error pattern is, and then add it to the received vector to get back the code word. You might be a little bit puzzled, how come you are adding, shouldn't you be subtracting? Yes, you should be subtracting, but the point is that when you are doing arithmetic modulo 2, it does not really make a difference whether you are adding or subtracting, and for that reason we add it back. Okay. So, again just to recap, the idea is that it is very clear from this picture here. Here is your received vector y, and then you are trying to decide the closest code word. By the way, I am interchangeably using x's and c's to represent the code word, hopefully that causes no confusion. So, you are trying to find that code word which is closest to it, which is equivalent to saying you are trying to find that distance vector which has least Hamming weight, and each of these difference vectors E1, E2 represent potential error pattern. So, you are trying to find the error pattern with least weight, and then you are going to add it back to y to get your estimated code word, and that is a slight shift in perspective, but a convenient one. Okay. So, now we have this. Now, there is one thing that I would like to actually bring to your notice here, that is this this set that I have declared over here, right. I have put down a set over here, and we have actually encountered this. We have encountered this way back in an earlier lecture when we were actually talking about cosets of a subgroup. Okay. That time we wrote the cosets in multiplicative form, whereas here we are actually writing it in additive form. So, maybe let us see, since we have the technology, why don't I take you back to that lecture so that we can take a quick look at that. Okay, here we had an example when we were talking about groups, cosets, subgroups, rings and fields. Then we had an example where we had the group was the set of integers mod 6 and H was the subgroup consisting of 0 to 4, and then we said that the cosets of the group partition the group, the subgroup. So, here the subgroup is H, which is 0 to 4, all the even elements, and then you have the even and the odd, and they partition it. Okay. So, right there we had introduced this notation H plus B. So, we are exactly the same situation where you have a subgroup which is the code, and then you are adding an element to it. Okay. So, hopefully that helped put things back in perspective. So, let us get back to our lecture. So, here, so the role played by H is now played by the code, and so it is in the same sense. Okay. So, we will just make a remark here. So, note that y plus c is a coset of the subgroup C of f2 to the n. If you look at the set of all n tuples, now that forms a group under addition modulo 2 component wise, and then the code C is itself a subgroup. In fact, all linear codes are always subgroups, we went through that, and therefore, you are looking at actually a coset. All right. And I think at this point it may be good to do an example, but there is another one other point I will make. Note that 1, so let us call this 1, okay, 2, and hence the decoder action is only a function of the coset of C to which y belongs, and not to y itself. Okay. The reason being that what you do is you form this set, and once you formed it, you find the least, the vector having least weight, which in this case happens to be e hat, and then you add that back to y. So, this is the action that is taken by the decoder. All that you are doing is you are adding e hat back, and this e hat is only a function to which of the coset to which y belongs, and therefore, the decoder action is only a function of the coset. With that in mind, let us take a look at an example. So, in our example, let C be the following code. Okay, so, this is the code, and in this case the parameters are obvious. The parameters n k d are given by 4, the dimension is clearly 2. It is easy to check that it is linear because you add any two code words and you get a code word, and the minimum distance is the same as the Hamming weight. So, from that you can easily see that the minimum distance is actually 2. So, this is a 422 code. Now, let us also, since we will need this a little later, write down a generator matrix for this code. So, a suitable generator matrix would be, remember, to construct a generator matrix, what you need to do is you need to set down a basis for the code when you regard the code as a vector space. So, it is easy to see that you can pick any two non-zero vectors in this particular case. So, let us, now I am also interested in trying to keep the generator matrix in systematic form. So, with that in mind, I will choose these two vectors over here. So, I am going to choose these two because they will lead, as you will see, to a systematic generator matrix. So, I am going to put down 1 0 1 0 0 1 0 1, And now I have my generator matrix in systematic form, where I have the identity matrix on the left, which is I 2, and I have the matrix P on the right. And we have already outlined an algorithm to find the parity check matrix given the generator matrix in systematic form. And actually it turns out that the parity check matrix, so in any case, so what you do is you would take P transpose, which would be 1 0 0 1, and then I, and so you find that in this particular case, in reality the parity and generator matrices are both actually the same, and that happens for a class of code known as self dual codes, but that does not need to bother us. Okay. That is just a coincidence which is of no consequence here. Now I am going to set up a table, okay, and that table is going to have 4 rows. So 1 2 3 4, so that is 1, and it is going to have 4 columns. And all right, what I am going to do is, in the top row I am going to put down the code words. Okay. So that is 0 0 0 0, 1 0 1 0, 0 1 0 1, 1 1 1 1. So these are the code words. So this then represents C, the code itself. Now I want to so what we are looking to accomplish is to implement minimum distance decoding in a very simple way, and this is going to help us do that. And I have already pointed out that the minimum distance decoder really cares only about the coset to which y belongs. So for that reason, what we are going to do is we are going to write down the cosets of the code. Now below this I want to reserve, now the number of 4 tuples is 16. So if you actually look at the set of all 4 tuples from an abstract point of view, then there are 16 of them, and so there will be a code, and then there will be 3 other cosets of the code. Okay. So you can partition this entire space into the code and cosets of C, the 3 other cosets of C, 3 other cosets. C itself can be regarded as a coset. There are 3 other cosets of C. So now we want to put down the cosets, but over and above that I want to actually put them down in a certain way, and the reason for that will become apparent in a little while. Now to identify a new coset, I simply need to start by taking some element which is not in here. So let me take I notice here that 0 0 0 1 does not belong to this, so I am going to bring that in 0 0 0 1, and I am now going to form the coset 0 0 0 1 plus C. Okay. And I am going to obtain the other elements simply by adding this vector to the corresponding vectors. So then that will give me 1 0 1 1, 0 1 0 0, 1 1 1 0, and I am going to continue in this fashion. I am going to look, and so I chose a vector of small Hamming weight here, and there is a reason for that. So I am going to continue to do that. Now I notice that I have exhausted one Hamming weight 1 vector here, another one here. So let me try another one which has not been taken up, 0 0 1 0. So then this becomes 1 0 0 0 0 1 1 1 1 1 0 1. So, then this coset is therefore 0 0 1 0 plus C. The last coset will be I have used up all the Hamming weight 1 vectors. So, I am looking now at Hamming weight 2, because I would like to start this off with vectors of low Hamming weight. So, I choose 0 0 1 1 plus C. So, I get 1 0 0 1 0 1 1 0 1 1 0 0. Okay. So, again the table is set up in such a way that you add the header, the column header to the row header. Okay. So, these are the row headers. Now, these vectors of least weight are actually called coset leaders. The vector of least Hamming weight in each column is called a coset leader. All right. So, how would you use this for decoding? So, let us try an example here. An example of decoding. So, let us say that y, now the code words are these vectors on top right here, right. You have 4 code words 1 2 3 4. So, let us say that for instance this code word was transmitted, and let us say that the third symbol got corrupted. So, meaning that y, what was received is actually 0 1 1 1. So, an error crept in the third symbol. Okay. So, now how does decoding proceed? The decoder says, look, I am interested in finding, my algorithm is, at least our formulation of the minimum distance decoding algorithm is to take y and then add e hat, where e hat is the least, is the vector of least Hamming weight within the coset to which y belongs. So, now I look for this and I notice that here this is a coset to which y belongs. So, y belongs over here, okay, and the coset leader is 0 0 1 0. So, what I do is I take 0 1 1 1 plus 0 0 1 0 to recover 0 1 0 1, and I have correctly decoded. Okay. Now, so this table makes decoding very easy to visualize, because all that you do is you pick your received vector out of this table, and then the vector to which you actually decode is the vector that is at the top of the column. So, for example, here was your received vector, this is your coset leader, you added and then you actually got back the code word which is at the head of the column. So, that is how decoding proceeds here, and that will always be the case. All right. Now, there is a further concept that we are going to bring in. Now, you notice that this vector e hat over here that we added to the received vector was a function only of the coset to which y belongs. So, if I could somehow identify from y the coset to which it belongs, then I can directly figure out what this e hat is, because in some sense if you look down this table, the set of possible e hats occur in this table. So, it is just a matter of determining. So, decoding or minimum distance decoding is just a matter of finding out which coset y belongs to and adding the corresponding coset leader. Again, just to emphasize, the way this table is set up is such that every entry here is the sum of the row header and the column header. That is how we set it up. Okay, that is important. Now, we will make an observation which is important. So, definition, the syndrome S associated to a received vector y is given by S is equal to H times y. Okay. Now, remember that this H is the parity check matrix of the code. For example, if y, now let us go back to what we had earlier here. So, we had y is equal to 0 1 1 here. So, let us go down over here and say that y is 0 1 1 1. Then, and we also know that the corresponding matrix H was given by 1 0 1 0 0 1 0 1. So, 1 0 1 0 0 1 0 1. So, we just have to simply compute the sum. So, S is equal to and you can easily see that this is nothing but the sum of the last three symbols. So, that is 1 and 0. Okay. So, this is the syndrome associated to this particular received vector. Now, the word syndrome is very similar in meaning to symptom. So, syndrome is like a symptom. So, just like a symptom tells you something about a disease, a syndrome tells you something about the error pattern. And as it turns out that for linear codes, the syndrome tells you all that you need to actually find out the most likely error pattern and therefore, the most likely code word. So, the key to that lies in this lemma. There is a one-to-one correspondence between the cosets y plus c of the code and syndromes S which belong to F2 to the n minus k, and I will explain that. So, back over here you notice that in order to compute the syndrome you multiply H by y, and we also know that this matrix H is an n minus k by n matrix. Okay. So, that is why this resultant vector will always have n minus k components, and that is the reason for putting n minus k there. So, proof first of all, so what is the map? So, we introduce a map which takes the coset y plus c and maps it to hy, which is the syndrome. And in mathematics, whenever you encounter situations like this, the first thing you have to check is that this map is in fact well defined. So, what does it mean to say it is well defined? Because when you talk about a coset, you can you are operating on phi by multiplying h by y, but this coset could also be represented by a different vector other than y. So, you have to make sure that no matter which vector you pick from the coset, you will actually get the same syndrome. So, suppose so the question to ask here is phi well defined? Okay. So, for that what you need to check is, suppose y prime also belongs to y plus c, the same coset, which means that y prime is equal to y plus c, where c is some code word in script c. And now we want to make sure that h times y or h times y prime does not make any difference, it is the same thing. Therefore, h times y prime is h times y plus h times c, but h times c is 0 for every code word. So, therefore, the same. And this is what we wanted to show. Therefore, it is well defined. Now, we want to actually establish more. We want to establish that in fact that there is a one-to-one correspondence. That is, the picture is something like this, that on this side you have cosets y plus c, and on this side you have syndromes. And what you are doing is you are mapping each coset to a particular syndrome, and you want to make sure that the map is one to one and onto. Now, a quick check will tell you that the number of possible syndromes is 2 to the n minus k. So, this set is of size equal to 2 to the n minus k, and since the set of all n tuples is partitioned into cosets by a code and the code has size 2 to the k, there are 2 to the n minus k cosets as well. So, you are actually looking at a mapping that is taking place between two sets whose size is the same. So, the only issue is, now is this one to one, or is it possible that for some other y1 plus c, which is a different coset, is it possible that some other coset will also be mapped onto the same syndrome? Can this happen? So, let us put a question mark. As it turns out, it cannot. Okay. Suppose phi of y plus c is equal to phi of y1 plus c. That is equivalent to saying that h of y is equal to h times y1, which is equivalent to saying that h of y plus y1 is 0, but that is equivalent to saying that y plus y1 belongs to the code, which is equivalent to saying that y1 belongs to y plus c. Or let me take this a little bit slowly, perhaps just so that I am clear. This is equivalent to saying that y plus y1 is equal to c, where c belongs to the code, which is equivalent to saying that y1 is y plus c, c in c. But then if y1 is y plus c, then that can only happen if y1 and y are in the same coset. Implies that y1 and y define the same coset, and we are done, because what we have shown is that the only way y plus c and y1 plus c can map onto the same syndrome is if in fact they define the same coset. So, it is not possible to have a picture like this, because the problem with the picture here is that here you are actually looking at two different cosets, but we have just seen that the only way two cosets can map onto the same syndrome is if in fact they are the same. So, they cannot be distinct. So, there is a one-to-one correspondence, and that correspondence is given by this. So, let us go ahead and see this in an example. So, what we will do is, for this particular code, we will go ahead and extend it. We will add an additional column here, and we will reserve this for the syndrome, which means what? We will actually compute h times y for any y in this coset. It does not make a difference. So, here for example, h times 0 is 0 0. Remember, this code has parameters nkd equals 4 to 2. So, that n minus k in this case is equal to 2. Okay. So, the syndromes are two tuples. So, now if I want to compute the syndrome, here is 0 0, here we already computed earlier and it was 1 0. We computed the syndrome here, found that it is 1 0, and in fact, so perhaps it will help if I, although it is going to crowd the screen a little bit, if I put down the matrix H over here. Let me use a different color which is slightly darker. Okay. So, if I want to compute the syndrome of this, I am going to multiply this vector by this. I am going to multiply this matrix into this vector, which means I will pick up the last column. Therefore, this is 0 1, and similarly here you can actually see it is 1 1. So, you see that there are 4 possible syndromes and there are 4 cosets, and each coset is associated to a unique syndrome. So, this is the map phi. So, how does that help in decoding? Well, now it is very simple, because if you have this table, then the rightmost column of the table gives you a syndrome for each of the cosets. So, what you do is you simply, given your received vector, your decoder does the following. First of all, it computes the syndrome by just computing h times y. Then from the syndrome it uses table lookup to determine the coset leader, which is called E hat. Then it adds E hat to y to recover the estimated code word. All right. And in fact, in this particular example here, we could have seen the decoding. We could have seen the decoding as being carried out like this. So, here is 0 1 1 1. We so in this, now I am going to view this as syndrome decoding, which means that given 0 1 1, our first step is to compute the syndrome, which is 1 0. Then we use the syndrome to actually look up the corresponding coset leader, which is 0 0 1 0. Then we add that back to the received vector to get the decoded code word. Okay. So, we have already seen an example of this, but just so that we are clear, let me write down the steps. This leads to the following simple implementation of the minimum distance decoding rhythm. And if you like, you can call this syndrome decoding if you like. Or standard array decoding. So, step 1, compute syndrome S, which is given by h times y. Step 2, use table lookup to determine E hat, which is the coset leader, associated to syndrome S. And step 3, decode to the vector C hat, which is given by y plus E hat, and you are done. So, in actuality what that means is, so let us go back a couple of frames. What that means in actuality is that to actually carry out syndrome decoding, you only need, you do not need this entire standard array, you actually need only the coset leader column and the syndrome column. Everything else you can actually do away with, because you can compute the syndrome and then jump by table lookup directly from the syndrome to the corresponding coset leader, add it to the received vector, and you get your decoded code word. So, the rest of it, so these middle 3 columns in this particular case were not really required. However, there is another use for the standard array, and we will come to that. Okay. So, that is our next topic. So, the next topic is performance analysis via the standard array. In this, so for this what we are going to do is I am going to go back to the standard array and I am going to reproduce it, but we are going to view it slightly differently. So, first let me select it. Okay. and now I want to copy it. And I want to set it down here. All right. So, here we have our standard array. Let me get rid of some unwanted entries here. All right. So, this is our syndrome, and let us also get rid of this line here. So, this is our standard array again. However, this time we are going to interpret the entries a little bit differently. Now, our earlier interpretation was that we view this as a table in which the received vector is one of these entries, and then to actually decode, what we do is we look at the row to which the received vector belongs, and then we look at the first entry in that row, and that is your estimated error pattern, and we add it back to the row, right. So, that was how we viewed it, but now we are interested in performance analysis. So, what does performance analysis mean? Performance analysis means that we are trying to determine what the probability of error of which is involved in decoding this code. Now, excuse me, this decoding algorithm is the best in terms of minimizing the probability of error. So, whatever the probability of error is, it is a consequence of the nature of the code itself. So, we are trying to say is this, what is the probability of error of this code when it is decoded to minimize the code probability of code word error. Okay. So, let us put that down. The goal in performance analysis is to determine the probability of error associated to the code. Now, this may actually sound a little bit vague to you, and I have actually deliberately left this vague, because you could say, well, what exactly do you mean by probability of error? Do you mean probability of code word error? Do you mean probability of message bit error? And there are so many different message bits, the probability of error of which particular message bit. So, the answer is that actually this standard array can be used to determine whichever one of these quantities or all of these quantities that you like. And so, that is going to be the next in the next lecture we are going to actually take this up. So, given that we have just about 2 minutes left, let me just summarize. So, what we have looked at in this lecture is a convenient implementation of the minimum distance decoder, and it is called the standard array decoder, and it leads to something which I have called syndrome decoding. So, the basic idea is that the minimum distance decoder only cares about the coset to which the received vector belongs. So, what you do is, as soon as the received vector comes in, you determine its coset by computing the syndrome, and then once you have the coset, you jump to the coset leader by using table lookup, and once you have this a coset leader, you add that back to the received vector and you get the most likely code word. So, you are minimizing thereby the probability of code word error. Now, what was I going to say? I was going to say that for moderate code length sizes, this is in fact a very practical algorithm. In fact, I myself have been enrolled in a project where this was carried out when we consulted for a certain company. And so, for reasonable block sizes, you can actually do this and therefore implement maximum likelihood decoding. It is only when the block length becomes very, very large, then this is no longer practical. Okay. So, anyway, I think that this is more or less a good place to stop, and the next lecture we will talk about performance analysis of a linear block code using the standard array. So, the array remains the same, except our perspective will change. Thank you.